Hello everyone, I'm Li Yaoli from University at Buffalo. Today I would like to present our paper, Cyclops, a nanomaterial-based battery-free intraocular pressure monitoring system inside contact lens. So glaucoma is a chronic and progressive disease that starts with a normal visual field. As the disease progresses, the vision field will gradually decrease until blindness. There is no cure for glaucoma. That's why it's been called the silent thief of sight. 3 million people in the United States and 80 million worldwide people are affected by the glaucoma. Glaucoma happens when the pressure inside of your eyes gets too high. It damages the optic nerve and causes visual loss. Eye pressure has a safe zone. Once the eye pressure is higher than 21 millimeters of mercury, it means high eye pressure. Our eye pressure changes throughout the days, so only continuously eye pressure tracking can help detect early-stage glaucoma. Continuously eye pressure monitoring is usually based on contact lens with embedded sensor. When the eye pressure increases, it stretches the contact lens, causing a slightly changes in its thickness. The pressure sensor will change based on the same mechanism. The pressure sensors are usually composed of ring structure with metallic structures. The impedance of these metallic structures vary with the applied pressure. Therefore, by measuring the variation in impedance, we can infer the eye pressure. But to measure the impedance of the pressure sensor, they need to connect the sensor to an expensive and bulky vector network analyzer through a wire or reading coil, which limited their communication distance with few centimeters. Also, this method requires continuously power through mutual coupling. So can we design a low-cost and battery-free contact lens-based eye pressure monitoring system that supports long-range communication? Here comes our Cyclops. Cyclops achieves long-range communication by integrating a backside communication system with a pressure sensor, all within this small contact lens. To design this system, first we need to find a sensitive pressure sensor with low power and micrometer level thickness that works on energy harvesting powered devices. Second, we need an antenna that supports long-range communication with contact lens size, also prevent block eyesight. We also have a challenge with potential interference between the communication antenna and the pressure sensor. Specifically, the metallic pressure sensor is designed to maximum the sensitivity to pressure changes, while the antenna is optimized to the efficiency and the range of the communication. If we directly place these two metallic components together with a pretty close distance, it will cause mutual coupling. This not only affects the pressure sensitivity, but also makes achieving long-range communication difficult. So we replace the metallic structure with a sensing layer embedded with nanomaterials and decouple the communication antennas designed from this sensing layer. Now let's take a look at our pressure sensor. We utilize the quantum tunneling effect of the hollow carbon sphere for our sensing layer. Here is the structure of our hollow carbon sphere. It's a good conductor and have a great stability and different environment, as well as good biosafety. We mix this carbon sphere with PDMS, which is the most commonly used material for contact lens and has a good electric isolator properties. The carbon sphere separated into the PDMS, forming a multiple layer structure with nanometer scale distance. Two hollow carbon spheres combined with the PDMS form a tunnel junction. Numerous electrodes distributed on the surface of the hollow carbon sphere. When the external electric field applied on the tunnel junction, the electrons will travel through the isolator and generate the tunneling current. The strength of the tunneling current is depend on the strength of the electric field and the distance between two conductors. In our case, the conductors are hollow carbon sphere. When the external pressure is applied on the PDMS, the distance between two carbon spheres will decrease and generate a stronger tunneling current. So we can measure the strength of the tunneling current to measure the applied pressure, right? But we seem to miss something. Remember, an external electric field is the essential for generate the quantum tunneling effect. So how can we apply this electric field on our devices? Normally, we can use two electrons to connect it with a power source and generate this electric field. But our system is battery-free. We don't have the power source. So we use two antenna layers as the electrons powered by the external electromagnetic wave and form an electric field between them. And this electric field will induce the tunneling current. However, the electric field generated by these two antenna layers is weak for generating obvious quantum tunneling effect. To address this, we make three optimizations to our system. First, we modify the carbon sphere into an earth-like hollow carbon sphere. The earth-like carbon sphere has a long, sharp, and uniformly distributed sparks on their surface. The electrons clusters on these spans form a stronger electric field between two hollow carbon spheres than the previous one. And the second, as we mentioned before, the strength of the tunneling current is related to the distance between two carbon spheres. So we can reduce the initial distance between two carbon spheres by increase the density of the carbon sphere inside of the PDMS. To further improve sensitivity, we add macrocone structure to the surface of the sensing film. This macrocone design is inspired by the leaves of Classia zebrine, which enhance the sensitivity of the sensing layer. After all the optimization, we enable the quantum tunneling effect with the basic structure of our contact lens, which consists with two antenna layers with a sensing film. We encapsulate it with two additional PDMS for biosafety. And we connect a commercial RFID chip to our antenna for backscatter communication. We use an equivalent circuit to represent each part of our system. The purple-colored component represents the antenna layers, and these layers are only these components' value are only related to the structure of the antenna. And we use a variable capacitor and a resistor to represent the sensing field. The impedance of the antenna is determined by both the antenna layer and the sensing field. Any changes in pressure alter this value of the variable capacitor and resistor, and change the impedance of the whole antenna. So we can measure the impedance by measuring the impedance variation of the antenna. So here comes another goal: how to achieve long-range communication. To maximize the communication range, it's very important to match the impedance between the chip and the antenna. When there is no pressure is applied on the contact lens, by carefully adjusting the structure of the antenna, we can match the impedance between the chip and the antenna. But when the pressure is applied, the impedance of the antenna will keep changing, causing mismatch between the chip and the antenna. So here comes another question: how can we match the impedance between the chip and antenna in real time? We give a solution by adjusting the chip's impedance through a self-turning circuit. This circuit acts as a variable capacitor and resistor, making the chip's impedance variable as well. However, the tunability of the chip is fixed. If the range of the antenna impedance change is smaller than the chip's impedance, it will waste the chip's resolution. If the antenna's impedance change range larger than the chip's impedance, it will limit the pressure detector range. Additionally, from the chip's tunability range, we can see that the resistance of the chip is spanned from 1 to 4 ohm, but the reactance of the chips is larger than the resistance. So here comes another problem. How can we design our antenna to concurrently optimize the communication and the sensing performance? We design a dual resonant frequency antenna. We created 2 resonant frequencies on both sides of the working frequency through antenna design. The structure's resistance has a flat slope, and the reactance has a sharp slope at the working frequency. This results in less responsiveness to changes in resistance and greater responsiveness to changes in reactance, which lies with the chip's impedance variation range. So the pressure changes the impedance of the antenna. The tuning circuit helps the chip to change the impedance to match the impedance of the antenna. By this way, we can not only match the impedance between the chip and antenna, but also we can measure this impedance because the chip will record how many impedances have been changed. And we can use a commercial reader to query this information from the chip. So here is our Cyclops lens, and I also put a picture of our Earth-in halocarbon sphere and our sensing film. We evaluated the end-to-end performance of our system. The communication range of our design tag reaches up to 1 meter. The accumulative error distribution of our system shows that 50% of the measurement error are less than 0.51 millimeter of mercury. Our system measurement accuracy surpasses that of the commercial portable eye pressure devices. We also explore our system's capability for both continuously and stepwise eye pressure changes monitoring. The red line represents the ground truth obtained from the absolute pressure meter, and the blue line shows the pressure data measured by our Cyclops. The median error for both scenario tests are 0.53 and 0.54 millimeter of mercury, which shows our system's ability to accurately track the fluctuation of the eye pressure. We use a pig eyes to test the biological impact of our system's performance because the pig eyes has the same structure and eye pressure changing mechanism with human eyes. We use a venous infusion tube to change the pressure of the pig eyes, and we change the distance between the Cyclops and the read antenna, and a different distance. The median error is 0.33 to 0.85 millimeter of mercury. We also examine our system's performance in various bioenvironments to explore the effect of the tears and eyelid. The median error of this eye pressure measurement is 0.5 to 0.6 millimeter of mercury in various bioenvironments. Finally, we attach the contact lens to the eyes of the pig to test the performance in a more real biologic environment. The mean measurement error of our system on the pig eyes is 0.97 millimeter of mercury, which is still more accurate than commercial portable eye pressure measurement devices. This is all for my presentation, and I'm ready here to answer any questions. Thank you.